In this video, we extend the concept of the integrated rate law to second order reactions for reactions that have only one reactant. So if I have a reaction that has just the one reactant and is second order with respect to A, then I could write that the rate of this reaction would be equal to the negative of the change in concentration of A over the change in time. And we can write that because the coefficient here is just simply 1. That would be equal to K multiplied by the concentration of A squared because it's second order. Now, if I integrate those two terms, I arrive at the integrated rate law for a second order process. And this is of the form y equals AX plus B, where my slope is equal to K, my intercept is equal to 1 on A naught when I'm plotting 1 on my concentration against time. Now K is always a positive number, so this will be a straight line with a positive slope. So for a reaction that is second order, if we plot 1 on A against T, you're going to get a straight line. The intercept will be 1 on the original concentration, and the slope will be equal to K itself. Pretty simple to do. So here's a example problem. It says ClO decomposes according to the following reaction. We see that there's just one reactant, so it gives us the opportunity to use the integrated rate law. And then it says the kinetics of the reaction was studied and the following data obtained. And it asks, is the reaction first or second order with respect to ClO? So what we need to do is plot log of the concentration against time. And if that is a linear with a negative slope, it would be first order. And in this case, you can pretty clearly see that it is not. Now to check whether it's second order, I'm going to plot 1 on the concentration against time, and if it is second order, that slope will be linear and it'll have a positive slope, and it is. So it is definitely second order. Now that's quite a lot of work, and I've posted 2 other videos, one that explains how to do this on your calculator without making any plots by hand at all, and another one that shows you how to do this with avoiding the plots by calculating a bunch of slopes. So if you're kind of struggling with making all of these plots in a timely manner, then I would encourage you to have a look at those videos, particularly the one that shows you how to do the whole thing on the calculator. So at this point, we've got the integrated rate law, and we can go ahead and get the rate constant because we know that for a second order process, the slope is just equal to K. So in solving part B, what do I have to do? I have to go to my plot of 1 on concentration against time, pick 2 convenient time points, and calculate the slope, and that's just going to be my y step over my x step, and that gives me my rate constant. Now notice the units for the rate constant for a second order process, it's concentration to the -1, and in this case my concentration was molarity multiplied by my units of time, and the time units are always raised to the power of -1 regardless of the reaction order, but my time units this time is milliseconds. Okay, so we can go ahead and derive an expression for the half-life for a second order process just like we did for a first order process. And so we know that when the concentration is equal to 1/2 of the original concentration, T1/2 has passed. So here's my integrated rate law for my second order process. When the time that's passed is equal to T1/2, then my concentration will be 1/2 of my original concentration, and my time will be T1/2. So I'm just going to kind of work through all of this. this is just bringing, instead of writing a half there, I'm just putting a 2 on the top line, and then I'm going to bring the concentration term over to the left-hand side, collect the like terms, and then finally divide by K. Now, what you see now is that for a second order process, the half-life is dependent on the concentration. And in particular, over time, the concentration of A will go down. And if we think how that affects the half-life, that means that over time, the half-life will get bigger. So sometimes you can look at your data and see if the half-life is getting bigger, and then that'll tell you that it's a second order process. Now the data has to kind of, regularly halve in concentration in order for this to work well. And if I go back to the data that was given here, it's like, it doesn't really kind of work out so great. So I can't really see that steadily halving. So I wouldn't be able to apply any of these simple rules in this case. Okay, so here's an example of calculating the half-life. It says calculate the half-life for the second order decomposition of NO2, given that the rate constant is 0.544 moles per liter per second, and the initial concentration of NO2 is 0.01 molar. And so it's just going to be plug and chug, right? T half is 1 on the rate constant multiplied by the initial concentration, and there we go. We're kind of, I didn't even do dimensional analysis here. 184 seconds. It's just simply applying the formula. But what's interesting is if we were to calculate the next half-life, so when the concentration was 0.005, it would be greater than 184 seconds. The half-life would keep getting bigger and bigger and bigger as time went on. Okay, so that concludes this section on second order reactions. There'll be another video on zero order reactions that's quite short, and also you might want to look in the resources. There's a couple of things up there. There's some problem solving strategies using your calculator that does all of the finding of the slopes for you and does all three plots that you'll need to do all in the one go. That's an awesome skill to figure out if you can. And then there'll also be a video there that explains an alternative to making the plots, which is by calculating a bunch of slopes in order to determine reaction order. But they'll be available for you in the resources.